Hi everybody, welcome back to the Feynman technique. Here's another integral I got off the channel Maths 505. Doesn't require Feynman integration. It is pretty tricky though. I might do another video where I introduce an x on the top there, and that would make it so that it would need Feynman integration to solve. But this one's difficult enough, so we'll just solve this. All right. Right away, I'm going to make the substitution that some new variable is equal to e to the x. And I'm not going to actually change the variables. I'm just going to write down what this integral would become. Let's see. E to the 0 is 1. E to the infinity is infinity. We'll have sine of the natural log of x. And then over, so this is going to be x times x minus 1. And then squared dx, right? Because, yeah, that's right. If we take x, if we take e to the x to x, that means x becomes natural log x. That becomes an x, that becomes an x. dx becomes 1 over x dx, right? That's right. Okay, so this is correct. All right, and now we're going to take x to 1 over x. So that's going to be equal to the integral from, let's see, 1 to 0 of the sine of the natural log of 1 over x over x to the negative 2 times x to the negative 1 minus 1, and then we'll have a times a negative 1 over x squared dx. All right, let's do some simplification. Let's see. This can become natural log x, but we need to cancel a negative sign somewhere. All right, we'll do it there. Okay, we'll let this x squared cancel with this x to the negative 2. We'll multiply the top and the bottom by x. We'll switch the order of this to make it x minus 1. And now we need to switch the bounds. There we go. All right. So those are all equivalent integrals. All right, now let's do something I've done 3 or 4 times on this channel. Let's set, or let's state that the imaginary part of x to the I is equal to the sine of the natural log of x. And that is because if you take e to the I natural log x, we know that this is equal to cosine natural log x plus I sine natural log x. But it's also equal to x to the I. Using the properties of logarithms, we can bring this in as an exponent on x, and then use the e to cancel out the natural log, giving us x to the I. And then if we take the imaginary part of all these, we'll see that the imaginary part of x to the I is equal to the imaginary part of this thing, which is just sine natural log x. All right. So that means we can write I as the imaginary part of the integral from 0 to 1 of x times x to the I, but that's just x to the 1 plus I over x minus 1 dx. All right, Now, let's we don't need to create a function of t, but since we have this thing right here, you know, I don't really want to work with that directly, so I am actually going to create a function of t, although, like I said, we don't need to. And our function of t is going to be equal to the integral from 0 to 1 of x to the t over x minus 1 dx. And then we can say that I is simply equal to the imaginary part of our function f evaluated at the point 1 plus I. Okay. All right, so now let's evaluate this using the fact that 1 over 1 minus x is equal to the sum as n goes from 0 to infinity of x to the n, and that's good on, let's see, negative 1 to 1 with negative 1 not being included. All right. Okay, so now let's rewrite our f of t. So that means f of t is equal to the integral from 0 to 1 of x to the t times the sum as n goes from 0 to infinity of, well, let's see, we have 1 over 1 minus x here, but we have 1 over x minus 1 here, so that's actually going to be a negative. We have to introduce a negative sign there. And this is just x to the n. And then dx. All right, we can bring this x to the t inside the sum as an exponent on x. And we can use Fubini's theorem to switch the order of integration and summation. So let's see, all in all, that's going to give us negative sum as n goes from 0 to infinity of, let's see, if we 1 over n plus t plus 1. Yeah, that's what it would be. It would be 1 over n plus t plus 1. All right. So now let's plug in 1 plus I for our t into here, then take the imaginary part, and we're done. All right. So let's see, that's going to mean that I is equal to the negative imaginary part of the sum as n goes from 0 to infinity of 1 over, let's see, that's going to become, if t is 1 plus I, that's going to become n plus 2 plus I. So we'll put n plus 2 in parentheses, and then we'll put plus I. All right. So now what we want to do is multiply the top and the bottom of this by the complex conjugate. We have some real part and an imaginary part. So we're going to multiply the top and the bottom by n plus 2 minus I. And in the bottom, that would just become n plus 2 all squared minus I squared, or just plus 1. All right. Now, since we're taking the imaginary part of this, we can get rid of this n plus 2 in the numerator, since it will result in a purely real part. We have to get rid of the imaginary part now, all right? And then we can cancel the negative signs, and this, in fact, this I becomes a 1 now because we took the imaginary part. And that's it. That's the answer, but we can do a little bit better. Let's start the index at 2 so that we can get rid of this plus 2 on the n, and we'll just make that an n squared plus 1. All right, and now let's, I want this index to start at 0 like it did before. So let's bring it down to 1. So basically we've just added the n equals 1 term because it wasn't there before. So what would that do? That essentially adds 1/2. So we have to subtract 1/2. Now let's bring our index down to 0. That had the effect of adding the n equals 0 term, which is 1. So we need to subtract it. So this becomes a negative 3/2. And that right there is the answer to the integral. This is some form of a diagamma function. I don't really get into those sort of special functions on this channel. In most cases, I believe a sum representation for an answer is good enough. In this case, it might not actually be, though, because this is not going to converge to that very quickly. You would have to add up, you know, thousands and thousands of terms in order to get close to the true answer to this integral. So I'm not 100% satisfied with that answer, but it is legitimate. If I is equal to this, then it's also equal to this. So anyway, that's it. I hope you enjoyed that.